ideas by physicists, very nice ideas. So they look at higher dimensional gauge theories, and and to these gauge theories, a lot of structures associated. In particular, VOAs are associated, in particular W-algebras, and even better, not only the structures appear, but the physics has dualities, and the dualities they translate to relations on the vertex algebra side. And the thing that I learned first, I learned it from Davide Gaiotto, so we also mentioned that name, that there are certain trialities between W-algebras, which in fact Andy Linshaw, who's there, and I studied a lot. If one takes these physics dualities seriously, then they in fact tell you a lot that about what should, hopefully, what should happen for VOAs. Anyway, somehow my picture is getting bigger and bigger, and I want to give somehow, I want to tell you what my intuition about the subject is, roughly speaking. So I'll give you a motivation now, then I will give you a theorem, and then I'll give you an example, and then we can all go for the reception. This is the plan. So I'm interested in the representation theory of a VOA, and the point is that the representation theory that one should, in this context, be interested in is you should be interested in a very general type of modules. So usually, if one starts with a VOA book and just what type of modules they construct, they put many niceness conditions on it, right? Usually, one looks at modules that are lower bounded. So conformal weight is lower bounded. Maybe conformal weight spaces are finite dimensional. For example, for an affine VOA, that would correspond to what we call the Kashtan-Lustig category. So that means each conformal weight space is just an integrable G module, an integrable module for the horizontal subalgebra. But in general, you can drop lots of conditions, right? And so, for example, conformal weight spaces, there's no reason to demand that they are finite dimensional. We know in category O already we have objects with infinite dimensional conformal weight spaces. But one can drop more. They don't need to be lower bounded. So then we are way out of the category O. And we also don't need conformal weight spaces. Generalized conformal weight spaces may be good enough. So for physicists, this all goes then under the name logarithmic conformal field theory, or then maybe logarithmic VOAs. And David is here also. He worked a lot on this type of representation theory. So if you want to learn more, talk to him or to me. Anyway, I'm interested in two questions. So first of all, if you have a VOA, so first of all you choose your VOA and you choose your type of modules, right? Certain bunch of niceness conditions, ideally not too many, so that you get a nice big class of modules. But then you wonder whether you can give this category a structure of a tensor category, meaning you naturally have intertwining operators on this category, but these intertwining operators, whether they define your braided tensor category structure. And this is a topic that has been pioneered by the Rutgers community, Huang and E.G. Huang and Jim Lipowski. And they have a huge amount of papers, and the point is, if your category satisfies a bunch of niceness conditions, which I list here, so then you get a braided tensor category. The problem with that is that you always have this condition that is called C1 cofiniteness, and that already implies that your modules need to be lower bounded in finite dimensional weight spaces. So for example, the work by Huang and Lipowski implies that for an affine VOA, the Kashtan-Lustig category has this structure of a tensor category. But you know, well, most modules of an affine Lie algebra are not in that category. So it's just a very small category. And So then there's the question whether one can go beyond this, and that's kind of tricky. And in fact, if you ask my type of community, what has been done, in fact, the last 10 years have essentially been focused on the affine vertex algebra of SL2, just because going beyond this category it's not that easy to get control about it. And in fact, I put this on the archive whenever I have time. A little paper where I say that the SL2 category in fact has a tensor category structure. And I can only prove this because there's a very nice duality to some superalgebra, a W superalgebra. So the correspondence to the W superalgebra is completely essential there. And I like this a lot because the way I now want to study affine VOA's W-algebras, I'm forced to include superalgebras because otherwise I would go nowhere. Okay, here is a slide with some notation just that I can give you the baby example of a duality that is maybe not that well known. So VKG will always, so G will be a Lie algebra or Lie superalgebra. VKG, the universal affine VOA, WKGF, the corresponding W algebra, the quantum Hamiltonian reduction with respect to your chosen nilpotent element. And then the next of 3 points take the special case of SL2 and SL2/1. So SL2 has the Heisenberg algebra corresponding to the Cartan subalgebra as a subalgebra, and you can take as commutant. So I denote this by CK. Similarly, the W algebra of SL2/1 is called the n=2 super Virasoro algebra, has also a Heisenberg subalgebra. So I can also take its coset as commutant. And the affine VOA of SL2/1 has an affine GL2, so I can also take the coset. So why do I introduce this notation?
If I may ask about previous slide, you say even nilpotent element. You mean nilpotent element which is even, or it is even nilpotent?
I should have phrased it a bit. A nilpotent element with it which is even, but it does not need
eigenvalues of H.
So it needs to be in the even subalgebra, but that's all exactly. But it does not need to be even in the other sense. I should have phrased that clear. Yeah, thank you. Okay, but what happened now?
Only go in one direction.
That's the problem. Yeah, thank you. These things are complicated. Okay, here I was. Okay. So at the bottom, you just can recall my notation if you have good eyes. So I introduced these 3 processes, and the reason I introduced them because they are all 3 isomorphic if your levels are related in a good way. So this relation should remind you of Hagen-Frankel duality, level plus the dual Coxeter number of SL2 times level of SL2/1 plus the dual Coxeter number of SL2/1. They multiply to 1. And this relation is probably less known, but if you know the GKO coset realization of principal W algebras, there you also have an isomorphism, a coset realization of principal W algebras, and the levels are related by this way as well. So, why am I showing you this? First of all, I wanted to give you a first example of a triality that is not that well known. So the well-known trialities are the Hagen-Frankel duality of principal W algebras and the coset realization of principal W algebras of type ADE. And it turns out there is a vast generalization, first conjectured by Gaiotto and Rabczak. And in fact, Andy and Ivy proved them. I actually note, for me, these trialities are so important because they help a lot for representation theory, or at least they help me to see what the representation theory of the VOAs should be. So I want to refine my first question. I not only want to, for a given VOA, I not only would like to have a tensor category, but ideally I also would like to understand what is this tensor category. And you know, a VOA is a complicated thing, but quantum groups are concrete somehow. And so I think the best thing one can wish for is one can show that your given category of modules of a VOA is tensor equivalent, braided tensor equivalent to some quantum group or some Hopf algebra or some quasi-Hopf algebra, something fairly concrete. And I want this talk, I want to present my point of view on this correspondence with this type of thing. So these, the name for these correspondences are Kashtan-Lustig correspondences, because Kashtan and Lustig, they had a very nice series of papers in the 90s where they proved that for almost all levels, the Kashtan-Lustig category, the category of modules of the affine VOA whose conformal weight spaces are integrable G modules, is graded tensor equivalent to the corresponding quantum group category. Right? And quantum group category where the Q, the shifted level is in the denominator here always. And it's now natural whether one can improve on this and whether one can improve in a few directions. Right now you can ask, can I take an affine VOA and can I go beyond this Kashtan-Lustig category and can I still get a correspondence to some quantum group? Or can I take a W-algebra and can I describe nice big categories that correspond to some quantum group? And so all these now fermate under the name logarithmic Kashtan-Lustig correspondence, just because I most often will get representation categories that are not semi-simple. And anyway, this is just a summary slide here. So I now want to present two conjectures that I have, and I very much don't think that they will be proven very soon, unless some of you are really, really good at it. So the first example is simply generalizing the Kashtan-Lustig correspondence to Lie superalgebras. Something very similar should hold, right? And so one would very much expect that if you take a Lie superalgebra that allows for a nice vertex algebra, and that are the basic classical ones, that then the category of modules whose the Kashtan-Lustig category, that means the category of modules whose conformal weight spaces are finite dimensional modules for the horizontal subalgebra, that enjoys some correspondence to the quantum supergroup. And it's in fact not hard to check for generic levels, at least, that you have an abelian equivalence. So so that's already a good sign. And in fact, if one talks about Lie superalgebras, one always should remember or should know that OSP1/2n, even though it's a superalgebra, it should be called a Lie algebra in the sense that its representation theory is really of that type. So, we are working on something different, but the corollary will be now. But now one would like not only go to superalgebras, but also to W-algebras. And these trialities of Gayotto and Creutzig that I mentioned at the beginning, they are concerned with what's called small hook W-algebras. So there's an orthosymplectic version and a type A version. Type A is always clearest to present, so I present it. So we take SLN plus M, for example, and we take a Young tableau with one column of height n, and then here m boxes. So that would be then, and to each Young tableau, you have a corresponding nilpotent element. So you think about SLN plus M, n plus M times n plus m matrices, and you have the upper block and n by n block, and there you put take the principal nilpotent element and 0 in the m by m block. And then you get a W-algebra, a quantum Hamiltonian reduction, which still has an affine GLM subalgebra. You can take its coset. And the Gayotto-Creutzig conjecture says if you take such a hook type W-algebra, you also have two W superalgebras of type SLN prime / M prime, where N prime and M prime are related to N and M. Always forget the precise relation. And their cosets are actually isomorphic to the cosets of this hook type W-algebra. And indeed, we were able to prove that this conjecture. So why do I say this? You always think about if you have if you take quantum Hamiltonian reduction, you always think about it, you have your Castellan-Lustig category of your Lie algebra, of your affine VOA, of your affine super VOA, and via quantum Hamiltonian reduction, that category should survive, at least at generic level. And if you think about that, think that through, then you arrive at a somehow very surprising conjecture, namely that these hook type W-algebras very, very likely have a huge category of modules. This will be modules that are not lower bounded, for example, but they will still be very nice module that should be braided equivalent to the Deligne product of many, many, many quantum group categories. Right? And one of them will be just the one that you get via the original Castellan-Lustig correspondent. All others will have the Fagan dual Q parameter, right? Because the shifted level is in the numerator, and really a huge zoo of them should appear. And yeah, it took me really time to realize this conjecture, and I think it would be really nice to make progress on that. And I think this is a very, very long-term project. But I have a conceptual way to approach these conjectures, and that's what I want to explain in this talk. Okay.
This side is just usual tensor product of associative algebras. You have.
Wait, the wrong. Yeah, exactly. It would be the usual tensor product of associated algebras. So yeah, you would say. I mean, I wrote it here in terms of the categories. But yeah. And then you can have more conjectures. There's also a triality for orthosymplectic type, and it's more technical to write down what it should be. But if you are interested in more general conjectures, I can tell you what they should roughly look like. And one can also go to roots of unity, and in the original Castellan-Lustig case, one, for example, knows that the Westomin-Witten models, the positive integer affine VOAs, they correspond to semi-simplification, so quotient of the usual quantum group categories, so quotients by all negligible objects. And here, in this more general case, one will have partial semi-simplifications. Just that means one just quotients by categories that are negligible with respect to the action of some subalgebra. So it's all interesting things that are appearing. Anyway, so my motivation is that if one is willing to go beyond this usual lower bounded modules, then a huge zoo of new interesting representation theory arises already if you are just looking at W-algebras, no super algebras, but the whole representation theory is intrinsically of super type. So super algebras are a necessity. Okay. And now one wants to have a good theory to approach these conjectures. And if you go over the recent progress on representation theory of W-algebras of this kind of type, you will stumble over work by people like Adamovich, Rideau, etc. And they, in fact, use very effectively that there are very nice free field realizations of the algebras. The famous ones are that affine VOAs enjoy this Wakimoto free field realization, some kind of chiaralization of invariant vector fields. And similar free field realizations hold for W-algebras. This is work by Naoki. Where is he? Ah, there he is. And it turns out that this is a really, really good tool for us. So what is a free field realization? A free field realization is an embedding of your vertex algebra of interest in a much, much simpler vertex algebra. So for example, principal W-algebras, they are just, they embed conformally, so they have the same Virasoro element. They embed conformally in a Heisenberg algebra corresponding to the Cartan subalgebra. Representation theory of the Heisenberg VOA, that's as easy as it can be. Right. So So here's the free field setup. So we think about, we have a VOA, we are interested in this VOA, we call the VOA V, and it embeds conformally into a bigger VOA, we call it A for algebra, and A has some known representation theory. Let it be Heisenberg VOA, then it's just graded vector spaces, or let it be, it could also be some rational VOA, Virasoro minimal model, for example, something that is simply known and easy to treat. Then we would say we have a free field or a generalized free field realization. And the question we ask is, how much can this free field category tell us about the original category? And the point is, this problem can first of all be phrased in a very clear language, namely in terms of algebras and category. So here I just, so that we have a definition, I wrote down what an algebra in a category is. So we have here a tensor category, then an algebra is an object, so we call it A. It has a multiplication morphism, it has an embedding of the tensor unit, and the multiplication has to be associative in the sense that this diagram commutes. Now, one can of course also then ask what is a commutative algebra, and a commutative algebra is if the multiplication is commutative in the sense here. So this C A, A denotes the braiding morphism in the category. And here now we recall that a category of VOA modules is a tensor category, and it's braided. That means it's commutative up to isomorphism, but it's not strictly commutative. Right? So these braiding isomorphisms are very non-trivial usually. And whenever one has a commutative algebra, then one has a category of A modules, and you call it UA. Sometimes people write rep A. This UA inherits a tensor category structure, but no braiding. In particular, it can't be a VOA category because a VOA tensor category is always braided. But it always has a subcategory that is braided. It's called the subcategory of local or dyslectic modules. Okay, and now the last years, there was a really nice article by Juan Kirillov and Lipowski, who noticed that the categorical language of commutative algebras and the tensor category is the same thing as the language of VOA extensions. And then we worked a lot to notice that this also translates to the tensor categorical language. This category of local modules is indeed the vertex tensor category, the tensor category defining operators. Okay. And so this means I rephrase my goal. So we have a free field realization, a VOA V that we are interested, for example, a W-algebra that embeds into a very nice VOA A, free boson, Heisenberg VOA, for example. And now, really, Heisenberg VOA is too trivial. We cannot recover our category of interest just from that. But but this UA might be a much more complicated thing, and maybe we can recover it from that. So the first question I now want to ask is how to recover the original category from this category of not necessarily local modules. And that has a clear answer. Before I present that, I also wanted to recall that free field realizations usually come with screening charges. And screening charges, if you know, screening charges have been a very big deal for people like Alyosha Semikhatov. And in particular, he has very much promoted the picture. So unfortunately, he left the fields, and he was ahead of his time. So he was always talking about the categories of Nichols algebras, and so he was always promoting that the screening charges should generate a certain algebra, an algebra in a category called a Nichols algebra. This is just an algebra generated by a certain module in your category, a nilpotent algebra, and he was always saying that these algebras should be exactly the algebra of the screening charges. And why is that so interesting? Because to any Nichols algebra, passing from a Nichols algebra to a quantum group is something fairly direct. So if you have a Nichols algebra in a category of graded vector spaces, so in the Heisenberg VOA, then from the Nichols algebra you can pass to what's called a category of Jetta-Drinfeld module. And these category of Jetta-Drinfeld modules, so these are certain categories of bi-modules where you have a kind of a left and a right action of your of a Borel constructed from your Nichols algebra. And then there is the Drinfeld double construction that tells you that this category of Jetta-Drinfeld modules is nothing but the category of modules of an explicit bi-algebra. In the simplest cases, a quantum group. And so I can now present you a theorem. The theorem says, under a bunch of natural assumptions, which I list here, and it's just certain assumptions we need in order for our argument to get through. So all these assumptions are not so difficult in practice to prove up to this annoying word, so that's unfortunately usually a technical issue. So our theorem says that once we have the setup, so that means we have a braided tensor category, the category of modules of our VOA V of interest, and suppose we have a commutative algebra that fulfills our assumptions, and then suppose we have a Nichols algebra in our category, then if we have a certain list of abelian equivalences, so this means if we can prove that our VOA category of interest is abelian equivalent to a category of some quantum group, which in practice is actually not that hard to prove usually, as long as we know you. If we know that our category of local A modules is the same thing as a category of graded vector spaces, well, that is usually for free. And if we know that our category of UA modules are not necessarily local modules, is equivalent to the representation category of our Nichols algebra as an algebra in the category of graded vector spaces, then all these abelian equivalents are in fact already tensor equivalents. Yeah, so this is our main theorem. Let me rephrase it. So what the theorem, so it says if you can prove a bunch of technical assumptions, which is the work that you have to do, and you can prove suitable abelian equivalences, and braided tensor equivalence of a very, I should have added many more of a very simple category, then you in fact get your tensor equivalences. And to give you an example, in the early 2000s, Gainudinov, Feige, they worked on something that we now call Feigin-Tipunen algebra of type SL2, and it is also called triplet algebra. And at that time, they introduced this algebras. These were kind of the first examples of VUAs that have a non-semi-simple and studyable representation theory. And they conjectured that category is tensor equivalent to small restricted quantum SL2 at root of unity. And that has been proven these years, so it took roughly 20 years to prove those. And getting the abelian equivalence has taken half the time, but that was more also because maybe not the biggest interest in, so that was really the first thing that was proven in that direction. Definitely getting this abelian assumptions was really not the hard part of it. And so I kind of, and I think it's also good to mention this here, because many of you are very good in studying abelian categories, right, Gobia? And yeah, and I kind of want to promote that, yeah, as long as you can do the abelian business, then you just have to prove the assumptions of the theorems, which a physicist would say, of course. Right? The assumptions are essentially that this VOA is sound in the sense of conformal field theory. So to give you an example, in 1988, Moore and Zyberg, they wrote a very remarkable and influential paper where they axiomatized the categorical features of a two-dimensional conformal field theory, and they basically defined what we now call a modular tensor category, and that was just out of the logic of two-dimensional conformal field theory, and it took E.G. Huang 15 years to prove that this statement is indeed correct. Yeah, so now let me just, I don't want to spend too much on the proof. I really want to give you one example of this, and that's it. But it's kind of a nice chain. So we have this categorical setup, and from that one can relatively, one can show that the category we are interested in is what's called a relative Drinfeld center of this category of UA modules. So UA, this is a category of, it's just a tensor category, and what people who are interested in braided tensor categories do, how do they find braided tensor categories? They take a tensor category and take its a Drinfeld center. It's kind of the double of the category, and that's always automatically a braided tensor category. And in this case, because we have already a braided tensor category, this category of local modules, that will be a subcategory of the center, so we can take its centralizer, which is called the relative center. And I will actually mention this, show a little bit more on this in the other slides. And then we are already in a good shape because just 2 years ago, Laugwitz, he explained how these relative Drinfeld centers are in fact equivalent to categories of Jetta Drinfeld modules. And going from Jetta Drinfeld modules to realizing bi-algebras is an old story. For a given example, it's an exercise to write down the generators and relations of the algebra and co-algebra, and as long as the rank is not too high, you can do it in a reasonable amount of time. So this is very nice. So maybe I'm not sure how familiar you're with the tensor category business. So here I just I'll tell you what the Drinfeld center is. So if we have a tensor category, then we can pass to the Drinfeld center. So in that case, the objects are pairs, an object together with a natural family of isomorphisms. So and these are called half braidings because for your fixed object, they go from x times z to z times x, and they satisfy the usual coherence condition for braiding, but here just for the half braiding. So that's called the Drinfeld center, and what we kind of our main categorical result is that under the assumptions that we have, one has always this equivalence, and then the rest is in fact known by other people. Let me maybe mention the technical difficulty. So the categories we are looking at are not finite. They, in fact, usually they have uncountable inequivalent simple objects. In fact, usually these categories are even wild, so it's hard. And in this type of business, usually if you want to prove an equivalence, you show that you construct your functor and you show that it's either fully faithful or essentially surjective, one of the two, and then the other statement also holds if the dimensions coincide, categorical dimensions for Venus-Perron dimensions. If it's not finite, you don't have a notion of dimension. And in this case, fully faithful, we could prove essentially surjective by hand. That didn't look feasible. And so the technical thing we achieved is that we were able to introduce a relative finiteness condition that also handled these infinite cases. So that's kind of nice. Okay, so all that is left is an example that you kind of maybe also you can now relax because it's a little bit more concrete. In fact, this example is also, one always goes back. So I did my PhD in physics, and it was on the branes and supergroups, whatever that is. Who knows? But the super, so it had to do with affine superalgebras, and that's not easy. So my focus was on GL1/1 because that's easy. And in fact, very interestingly, my very first talk I gave in my first year of PhD, and I gave it here on GL1/1. It's very nice, and it's my second time I'm in Edinburgh. Okay, anyway, that's all not. Yeah, so GL1/1, this is 1/1 super matrices, and yeah, definitely the least super algebra that is best behaved, even though it's not a simple one. It in fact also has found its application in low-dimensional topology, and it was not the first one, but maybe the third. So also physicists had quite a lot to do with it. But somehow for all these things, it's just because they are technical, and maybe also we are not so many people in the community. It took us a long time to put these things on rigorous footing. Anyway, so so we have now 1/1 times 1/1 dimensional supermatrices. So the diagonal matrices are the even ones. So the even subalgebra is just abelian, two-dimensional, and then the odd part is also two-dimensional, the two off-dimensional, off-diagonal and diagonal ones. And the only non-trivial commutation relations are quickly computed. And now we can first, so you can really relax because now it's very explicit. We can now construct modules. Well, what do we do is, so here in this case, very nice, the even subalgebra is also the Cartan subalgebra, right? And so what do we do is we take a one-dimensional module for the Cartan subalgebra. So this means n acts by n, e acts by multiplication with lowercase e. And then we make it highest weight by saying one of the odd elements annihilates it, and the other one acts freely. Well, it's odd, it squares to 0, so it will generate as a two-dimensional module. So the Verma modules of GL1/1 are all two-dimensional. And now you can think about it. You have this two-dimensional module generated by a vector, and one of these odd elements applying it to it. Now you ask yourself, can you go back? Well, because of the commutation relations of because of the commutator of the two odd elements gives you the central element. You immediately say, well, you can only go back if the central element acts not trivially. And so what you get is all these Verma modules are irreducible except for the atypical series when e is equal to zeros, where you have a one-dimensional submodule and a one-dimensional quotient. Now you can ask yourself, so usually if you want to study the abelian category, ideally you want to have a complete list of inequivalent simple modules. Ideally you would like to have a complete list of of the projective covers of the simples. Really. So these Verma modules that are simple are also projective and injective all at the same time. But whenever this E is equal to 0 in this atypical position, these one-dimensionals, they allow extensions with 4 composition factors. So you read it as this projective module has a one-dimensional submodule. The quotient is a direct sum of 2 one-dimensionals, and then the top component is again a one-dimensional module. And these types of modules, they appear in many other categories. For example, if you look at small quantum SL2 and any of its version, they also have these kinds of projective modules. Okay, now once we know what, this is already all I need to present about the representation theory of the finite dimensional Lie superalgebra. And now if you affinize, well, you do it in the usual way. So here, and then the zero mode subalgebra, so our horizontal subalgebra is just GL1/1. And now what can we do is we can, of course, induce any module of the horizontal subalgebra to a module of the affine Lie algebra, and then you can ask yourself whether the induced modules have the same structure or not, and the answer is almost the same. So it turns out if you induce one of these generic Verma modules, it will almost always stay simple and projective. It's just that you have a certain additional discrete series. So here now this M can be any integer. For the finite dimensional one, it could just be 0. Where this affine Lie superalgebra has also this type of projective module, but same type of composition factors. And if you look at the literature about quantum GL1/1, it's probably easier to do it yourself than finding it in the literature. You would quickly compute that representation theory of the quantum group of GL1/1 is exactly the same type. So the abelian equivalence is obvious, and studying the quantum group is an explicit exercise. Okay, now once we have the affine Lie algebra, we can of course go to the VUA. I'm just here repeating a few things that probably most of you know, right? So for the affine VUA, it's strongly freely generated by fields corresponding to a basis of the underlying Lie superalgebra, and the OPEs are accordingly. Okay, now now one can kind of keep this OP in you can keep it in your head, and you can wonder, can I construct find a free field algebra in which this VUA embeds? And it's so simple that probably with a lot of trial and effort you would come up with a formula like this, but really you don't have to try, right? Because you the old work, the Wakimoto free field realization, caramelization of invariant vector fields works equally well for superalgebras, and it's just that now in this case the ghosts that you introduce, they are odd fields here because you have odd differential operators, and then the caramelization tells you that you get a free field realization of this type. And with that, we have reached the setup of the theorem that I wanted to introduce. Right? What did I say? In the theorem, I said we are interested in a category of modules of a VUA. So here's the affine VUA of GL1/1. And for that, we need a conformal embedding into something very simple. But what can be simpler than a pair of a rank 2 Heisenberg times 2 free fermions, right? The category of modules of free fermions is just super vector spaces, and the Heisenberg gives you graded vector spaces here, and then C2 graded vector spaces. And we even get more information, namely this embedding is characterized as the kernel of a single screening charge, and it's just the zero mode of a very explicit intertwining operator. So it's okay, and so this means the free field algebra is nothing but rank 2 Heisenberg times free fermions, and of course any simple module for the Heisenberg VUA is just a Fock module. The tensor product, the fusion product of Fock modules is just addition in the label, and the only thing that is non-trivial is that If you swap the order, then you of course get the same module, but you have a non-trivial isomorphism. The braiding is non-trivial, but it's completely characterized by a quadratic form, which is in fact a quadratic form. So this means if we go back to our old setup, we have this category U that we are interested in, this category of modules of the affine super VUA GL1/1. We know what it is as an abelian category, and we know that it embeds conformally in a VUA whose category is as nice as it, I wrote as easy as it can be. As it is, right? It's the nicest type of tensor category. And so this means if we now were able to find out what this UA is, then we immediately would get by the theorem, get a correspondence to some Hopf algebra. Okay, so now we have this screening operator. It's just the zero mode of an intertwining operator. In this case, one quickly computes its squares to zero, so it's nilpotent. And moreover, it's an intertwining operator that is naturally associated to a certain module. So it has a certain weight. So so it's kind of naturally identified with the algebra generated inside the category of graded vector or the supercategory of graded vector spaces, and the algebra generated by the module X of grade of weight alpha, subject to the condition that it squares to zero. Now to this thing you can, and now you can study the representation category of this Nichols algebra. Well, kind of very simple, right? Because what can you do is you take a simple module in your underlying category, just a Fock module times your free fermions, and then what can this Nichols algebra do is it can only map this to the corresponding next Fock module, because it has weight alpha. It only changes the weight label by alpha. That's all, and because it squares to zero, it can't go any further. So this means you can immediately construct what you should call Wörmer modules for the Nichols algebras, and they are just extensions of Fock modules by a single simple additional Fock module. And there's a specific relation between the weight labels. And that's already it. The representation category of this Nichols algebra has as simple objects just the Fock modules times the free fermions. And these simple objects allow for extensions by a single further simple object, and these are then already projective. So it's so understanding the category of modules of the Nichols algebra is kind of it is obvious the moment that you know that it has squares to zero and which weight it has. And if you do an analogous problem where you want to get your quantum group of a certain root of unity, say 2p root of unity, then you would get a Nichols algebra where your generator doesn't square to zero, but the pth power of zero. Okay, and so now the point is one can now explicitly also compute what this UA is. So that it is in fact a longer computation, 2-3 pages, but really, but also nothing more. And then and the result of that computation would be, well, that this Nichols algebra category and this UA are in fact equivalent as abelian categories. And that's all one needs in order for the theorem to conclude that actually the VUA category is this relative Drinfeld center, but this relative Drinfeld center is a category of Jetta-Drinfeld modules, which is realized by some Hopf algebra, and in this case it turns out it's the quantum group of GL1/1, and this H just means it's somehow unusual Cartan subalgebra. It's also called unrolled. And that's it. And that would be that's the illustration of how the theorem that we have tells you that indeed the Kashtan-Lustig correspondence for the affine algebra of GL1/1 poles. So it's kind of the baby example of the conjecture that I would like to prove. And it's also the nicest one for illustration. So what I wanted to tell you, and I have mentioned it a few times, I wanted to say that if you have a nice realization of a VOA, meaning these free field realizations, let it be a Wakimoto, let it be a Genra realization, one of these many realizations that we have now, then as long as you can prove a series of technical assumptions, and if you can prove in addition abelian equivalence, then you're good, because then you get a tensor equivalence to some nice algebra, bi-algebra, some Hopf algebra. And often enough, this will be a quantum group or a variant of a quantum group. And yeah, now here I have 2 slides with a bunch of examples. Just so the unfortunately, it's just very hard to verify these assumptions, and these examples are all the cases where we can verify the assumptions, and then you immediately get something. So the first case is in fact the one we wanted to prove with our theory. So it's a conjecture that I think goes back to Constantino Diapatiro and Miron. So they are the people who made most progress on studying non-semi-simple 3-dimensional TQFTs, and they do it exactly by attaching these TFTs to category of modules of quantum groups like this. And so we prove their conjecture. There's also an analogous one for the triplet VOA, so that would be the original Semicator-Bagan conjecture that was also proven by Gannon and Negron. And then we have other examples. For example, there we have a series of principal W superalgebras of type SLN/1, and we find a very specific Hopf algebra that realizes it. This Hopf algebra looks like it has nothing to do with SLN/1, but you can in fact show that it's one of these partial semi-simplifications. So it's at a very small root of unity, and so that means for the even quantum subgroup, the quantum group of GLN, almost all objects are negligible, and then it becomes a very and that makes it somehow hard to notice the quantum supergroup. And then there are more examples. I'll actually stay quite a bit here in Edinburgh, because Tudor and I, we will talk about how quantum groups appear also in physics, so this will be a lot of fun. And what I will focus on, I think, on Cauchy-Lustig correspondence for type 1 Lie superalgebra. So type 1 allows for super nice free field. The Wakimoto, there's a relative Wakimoto realization that is perfect for proving it. So this means that's in fact very realistic to prove that correspondence there. Yeah, very good. Thank you for your